Echo, echo, echo. I call that a successful mic check. Okay, so here we are. It's Friday afternoon. Friday afternoon for me, anyway. And this is something I've wanted to do for a while. And earlier this week, I finally got the guts to actually do it. So, what I've wanted to do for a while, that I just referred to, is to do kind of a short video series on the Atari 5200 and how you program for it, and give a general explanation of the system architecture, how it works, some of the programming techniques involved, just to get people interested in doing it for the system. Because, as a lot of people point out, I'm kind of the only person writing games for the system right now, more or less. And I want other people to do it. I keep releasing all my source code, hoping someone will pick it up and say, oh, this is cool. I'm going to write a 5200 game. Well, nobody's doing it. You people are letting me down. So I'm going to have to just teach you people how to do it. So my plan for this is to write a very simple 5200 game live week by week. I don't know how long it's going to take. I've only very, very roughly planned this thing out. But what I want to do is sort of a kind of a Space Invaders type game with a player at the bottom shooting up at things flying around in the sky. It'll probably end up being more like Demon Attack than Space Invaders, but it's a very interesting thing to show a lot of the mechanical aspects of how the console works, how you'd achieve different things, and it might serve as a catalyst for somebody to go out and do something great on their own. Or maybe not. Maybe people just watch this and point and say, oh, that's interesting, and then move on with their lives. I have no idea. But one way or the other, I intend to do this. Now, I may continue after this project is done and do another project, because it's very difficult to show the whole range of what the 5200 can do in the scope of one project, especially with the Antic chip and all the different modes it has. But I'm getting ahead of myself. So before I go any further, I should probably introduce myself and talk about why I just might be qualified enough to do this. So my name is Ryan Whitmer. I write PC and Atari games. So far, just focusing on the 5200, but let you in a little secret. I've been playing with the 7800 lately, but the 5200 is still my first love. And I have had 4 games published by AtariAge.com, and I brought props. So there's my 4 games. Count them, 4 cartridges. And I have a 5th game that's pretty much done. It should be released next month at the Portland Retro Gaming Expo. And just in case anyone's watching this video after I post it to YouTube, at the time of this recording, next month is October of 2022. So not a lot of time between this recording and that game actually getting released. But having written 5 games for the system, I feel like I can probably give some pointers on how you do things. Now, I am, of course, 100% self-taught, as a lot of the programmers that do this stuff these days are. So if some experienced Atari programmer comes along and looks at what I'm doing and says, that's stupid, you should do it this way, you should probably listen to that person. But you can look at what I'm doing and at least give yourself a general idea of how this stupid thing works. Now I'm going to go ahead and kill this emulator window, which I had running just to make sure everything was kind of on the level here. If I can remember how to quit it. Exit. I've lost my mouse cursor. Where's my mouse cursor? There it is. Okay. All right, so a little bit about tools here. So in order to develop anything for the system, the first thing you're going to need is an assembler. So the 5200 uses the venerable 6502 processor as its main CPU, and I work in assembly directly. I'm sure there are other means of writing these if you look around and poke around for them. But even if you do use a higher level language, you still need to understand how the system functions in order to get the most out of it, or sometimes even anything out of it. So I will be working in assembly, but I do want to make it very clear that the purpose of this video series is not to teach 6502 assembly. There are much better places you can go to learn that. I want to focus on the 5200 itself rather than getting into the details of assembly language. Now, that's not to say that I'm just going to blow through and assume everyone knows 6502. I will probably stop every now and then and point out weird little gotchas and things you need to know about 6502, because if you're using this as something to assist you in learning that assembly language, you're probably going to run into these problems. So I will point out some things here or there, but for the most part, this is not where you should come to learn 6502. I'd recommend going somewhere else for that. As Arthur C. Clarke once said, watch the movies, read the books, repeat as necessary. So if this gets you interested, go find a 6502 site, learn a few things about the assembly language, come back, watch this again, and see how much more of it makes sense to you. So, enough about that. Now, the assembler I use is called DASM. That's spelled D-A-S-M. Looks like that. DASM is free. You can find it. It's available for just about any platform you can think of. I'm one of those weird Linux nerds. I'm on Linux right now, so that's kind of the development I use. Now, you also need something to write assembly code with. Any old text editor will do. I'm very much an old school Unix type guy. I just use a plain text editor, specifically Vim, to do all of my assembly, so that's what I'll be using here. But there are many other fancy development environments and all kinds of stuff you can find if you look around. I really can't recommend any because I don't use any, so my recommendation would be worthless. But I'm sure someone can point you in the area. Ask your local expert, as the Unix docs always like to say. So, you get yourself an assembler, you get yourself a text editor, then you need a way to run your program. So that usually means an emulator. I'm using an emulator called Atari++, which I'm actually in the process of moving away from because it definitely has some bugs, and some of those bugs have started to cause problems for me. And I've been moving toward another assembler called Atari 800, but I'm not there yet. So for the purposes of this video series, I'm going to continue using Atari++, because that's what I've been using up to this point. My next real 5200 project, I'm going to migrate to Atari 800 and start using that instead. But I'm not there yet. So whatever platform you're on, look around, see what emulators are available. I really can't recommend them because I found Atari++ and that's all I've ever used. So I'm not a good source for recommendations on emulators. Now, when it comes to assemblers, if you end up using an assembler that's different from DASM, some other assembler, the code that I write here will mostly be compatible. There will probably be some little things here and there that don't work, and you'll need to figure out how to fix that, and that just depends on what assembler you're using. I really can't offer any advice on that, but for the most part, everything I do here should work okay. So, that being said, let's talk about code. So, in a project of any size, you're going to want to break the code up into several files just for your own personal organization, if nothing else. And I do usually do that, but I think for this project, I'm going to keep everything in one file just to avoid any confusion. Now, I've already created this file. I've named it 5200lesson.s. .s is the typical extension for assembly files on Unix systems. If you're on other platforms, it might be .asm, whatever. It doesn't matter. Use whatever you like. So this is the one file we'll be putting all of our source code in. Now, there is another file I'm going to be making use of here, and that is a file I've written, and if we go back here, you can see it. It's called hardware.s. So here is hardware.s, and this is actually where I want to start today, is right here with this file. So from what I have seen, when it comes to developing for these old consoles, if you download some stuff to work with one of these consoles, you're going to find a file similar to this almost every time. What this file has is a bunch of symbol definitions for various locations in the console that are important. Now, I have built this one myself personally because I like to build my own files for this because I like to do things in a very specific way. And like I said, I'm learning the 7800 right now. There are files like this for the 7800, but I said, no, I'm doing my own. So I have my own hardware.s for the 7800. But it really doesn't matter where you get it from as long as it's right. Now, the names of these locations are pretty much standard. There's a few here that probably aren't that I've had to make up on my own. But when it comes, the 5200, if you don't know, is actually, for the most part, a modified Atari 400 computer. The hardware is essentially the same. And if you were to go look up some Atari 400 programming documentation, these are the names you're going to find. Because almost all this stuff is on the Atari 400 or 800 or XE or whatever. I don't even know the computers that well. But it's fundamentally the same hardware, which is one of the interesting things about the 5200, because it's really easy to find documentation on, because there were tons of computer books published about those computers back in the day. And there are archives online you can go to and find information. So if you go find a book excuse me, on Atari 800 programming or whatever, most of the stuff you find in that book will apply to the 5200. Now, there are some exceptions, of course. The biggest one is input, controller input, because I've got another prop here. The 5200 controller, this baby, is completely different from what's on the Atari 8-bit computers. Sort of. That'll make more sense when we talk about input. But if you were to work from an Atari 400 book or whatever, the section on input you need to seriously change. Now, let's talk about what's in this file, because what's in this file gives a pretty good overview of the 5200 console, what its parts are, how they work, and stuff like that. So I want to just very quickly go over this without trying to dig too deep into various parts of this. Now, the first section I have here is helpfully labeled page 0 stuff. So here's my first quick segue into 6502 speak, just in case you're not familiar with this processor, because I don't know how common these terms are in other assembly languages. Like maybe Z80 uses these same terms. I really have no idea. But, so what does page 0 mean? So the 6502 uses 16-bit memory addresses. So that's 2 bytes. And when written in hexadecimal format, and I'm absolutely not going to explain hexadecimal. If you don't know hexadecimal, go learn that and then come back. But in hexadecimal format, a 16-bit address is going to be 4 digits long. And the first 2 digits, which constitute the first byte of the address, are called the page. So this address right here is on page C0. These addresses here are on page D4, and so on. Now, what the second byte is called, I have no idea, but I may not even have a name. But page 0 is the first 256 bytes of memory. It's the addresses that start with 00. But you notice here, I don't have 4 digits here. These are all 2 digits. And the reason for that is because the 6502 has an address mode where you can give it a 1-byte address. And it understands that that means page 0. So you don't need to supply the second byte of the address. The reason why this is important is because a page 0 address, any instruction that accesses it, typically ends up being 1 byte smaller because it only has an 8-bit address instead of a 16-bit address, and will also typically execute 1 processor cycle faster because it doesn't need to load that second address byte. This is not universally true. I'm pretty sure there are a few instructions that don't have the page 0 addressing mode, but most of them do. And both of those properties are extremely important in certain situations. In fact, my third 5200 game, this one here, Magical Fairy Force, which I would be remiss if I didn't point this out, this fantastic shirt I have, because the PC version of this game has just showed up on Steam. It's not available for sale yet, but it's there. So please go check it out. But this game, I was running out of space on this game. And toward the end of development, I took a bunch of data and moved it to page 0, and suddenly I had 512 bytes back. And if it weren't for those 512 bytes, that game doesn't get finished. So the space and the time savings of page 0 instructions are very real and very important. So generally speaking, you want to put as much of your data on page 0 as possible. But you kind of have to prioritize at the same time. So if something isn't very frequently accessed, it's probably not worth putting there, because there's something better you could put there. But that's a topic for another time. But the point of this here is that the system BIOS reserves a large chunk of page 0 for various things that it does. And that's what all of this is. Now, this is not a complete list. I kind of add things to this as I need them. I can see already I'm missing address 03, which out of curiosity, I went and I looked up, and it's something called the critical code flag, which I've never used in my life and probably never will, but that's what it is. But the point is, all of these addresses up through address hex 18 are reserved by the BIOS for specific purposes. So you never want to stomp on this area because these addresses mean something. Now, everything from hex address 19 all the way up to the end of page 0 is completely open for you, the programmer, to do whatever you want with it. But hex 18 and below, those addresses you can't mess with. And we'll talk more about what some of these things are later. Now, I immediately go up here to page 2, but what about page 1? I do want to talk about page 1 very briefly. So page 1 is where the 6502 keeps its processor stack. I'm not going to go into what the processor stack is. That's processor theory stuff that you should go research on your own. Definitely important to know in the long term, but that's where it is. It's on page 1. So generally speaking, don't ever touch page 1 unless you really know what you're doing. I don't think I've ever written a single bit of code that's ever touched page 1. Leave it alone. Now, page 2 also has some reserved stuff on it. And I know for a fact this is also an incomplete list. I went and actually looked up the complete list of reserved page 2 areas, and it's about twice as long as this. But this is a jump table to various interrupt handlers and things like that. This is a very important area right here at the beginning of page 2. I don't remember exactly where this ends. I would say, but just stay away from the beginning of page 2. I do frequently use the end of page 2 to store things, but page 2 up to roughly address, I'd say hex 210, I think is roughly about where it stops, is all reserved for these very specific things. And we'll talk about these again a little bit later. Now, moving further down the memory map, we get here to GTIA. I don't know if people actually pronounce this GTIA. That's what I call it. I don't care. That's my name. It's my show. So GTIA stands for Graphics Television Interface Adapter. This is the chip that's responsible for actually producing the video signal that comes out of the 5200. The TV signal, I think, is a better way to put it. At least I think. I don't know when the audio gets mixed into that. But you know what? I've written 5 games without knowing that, so it doesn't really matter. But either way, the GTIA is responsible for generating at least the video portion of the television signal. And the various areas, registers, as they're called, various inputs and outputs on this chip, all appear in this on page C0. So that's where it's mapped to. Now, one thing you might notice if you're looking at this is that these two things right here both have the same address. They're both at C000, which is a little weird, huh? So many of the locations on the GTIA have different meanings depending on if you're writing to that address or reading from that address. So in this case, this address here HPOS P0 stands for Horizontal Position Player 0. Player 0 is one of the objects you can place on the screen. So if you write to this address, you're setting the horizontal position of Player 0. If you read from this address, you're getting this, M0PF, which stands for Missile 0 Playfield. This is a collision register, which tells you there's another object called Missile 0 and another thing called the playfield. And this tells you if that missile has collided with the playfield and exactly how it has collided. So this location means different things if you write to it or read from it. And you can see this pattern continues through a lot of this chip. So expect to see that quite a bit. Now, GTIA is essentially the next generation of the TIA chip that drives the 2600. It operates in much the same way. It's just bigger and better. Now, the next thing we run into here on page D4 is Antic. Antic is another video chip, and the main role of Antic is to take a lot of the work that 2600 programmers had to do and make it so they don't have to do it anymore. So, quick description is that on the 2600, you would configure the TIA to draw a single scan line across the screen. And then after that scan line ended, but before the next scan line started, you'd have to go in and change the settings in TIA to configure it for the next scan line. And you have to do this all the way down the screen. And the code that does this, the 2600 people call a screen kernel. So if you ever hear anyone talking about 2600 screen kernels, that's what they're talking about. This is a lot of work and it's a pain. The Antic chip relieves you of most of that burden, because the GTIA still requires something to do that. But Antic does most of that for you. Not all of it. There are sometimes you will still have to jump in and play scanline games, but most of the time Antic will do the heavy lifting, and we're all very happy for that. Now, the final chip we have here is Pokey, which is on address E8. Now, if you're coming from the 7800, you probably think of Pokey as a sound chip, which always kind of bothers me because Pokey is really primarily a serial input-output chip. That's where its name comes from. It stands for potentiometer keyboard. It's made to scan input. the fact that it does sound is really kind of a secondary function. But 7800 people, man, that's all I care about is Pokey sound. Well, on the 5200, you're going to probably care more about Pokey's input functions than its sound functions, because Pokey does most of the controller scanning. There's actually one thing that Pokey does not read, which is actually read by GT of all things for historical reasons, I'm assuming. We'll get to that later. But yeah, so Pokey does most of the joystick scanning and is also the sound chip. And you can see it also has a lot of these same type of registers where you have two things at the same address, where read and write do different things. Now here we have BIOS locations of note, and Vim feels the need to highlight note. So these are various locations in the system BIOS, which is located way at the end of the address space. You can see these addresses are very high addresses. These are different interrupt handlers. Now, I think these might be my own names. I don't know if these are standard names or not, or if I made them up. And I also suspect that on an Atari computer, these probably would be completely different, because that has a totally different BIOS. But these are various locations in the BIOS chip that we're going to make use of. And so I've gone ahead and named them so I don't have to keep remembering their addresses. But I don't think I'm ever going to forget FCB2. That's just burned into my head, because that's the one I use the most. And here I've created some constant names for some of the keys on the keypad. Don't worry about that for now. And just my own little helpful guide to color codes. But this is, just a very brief overview of the hardware in the 5200 and where it lives at. And I do want to mention that one of the big differences, and it's not a super big difference, between the A8 computers and the 5200 is that two of these three chips are on different pages in the Atari computers. But I can never remember which two it is. But it's just the page number that's different. The addresses within the page are all the same, but they're just on different pages. I think Antic is the one that's in the same place, but I'm not really sure. But anyway, there's your overview of the hardware. Good coffee. All right, so let's go ahead and get something started. So this is the 5200 lesson.s file I've created. And the first thing we need to do is worry about, how do you start this system up? How do you even get anything going on? Well, let's do that. Now, the first thing you need to do, and this is a DASM thing, is that the DASM assembler assembles a variety of different processor types, all of a huge number of old processor types. So if you're going to run a source file through DASM, you need to tell it what chip this is supposed to be so that it knows how to assemble it. So the first thing we're going to put in here is processor 6502. That tells DASM this is a 6502 file, so it knows how to assemble it. Now, indentation is important here. This is not just window dressing. Assembly files are very sensitive to indentation, so you need to make sure you do it correctly. If you put this all the way against the left edge, it becomes a label, which is something totally different. So remember that. Now, next thing I'm going to do is pull in that hardware.s file. So this include directive here actually just copies and pastes that whole file right there, so all those symbols will be visible in the rest of the code. Very important. So the first thing your cartridge needs to do is to set up its reset vector. So when you first power up a 5200, the code execution actually starts in the BIOS. There's a BIOS startup routine, and that's where everything starts. But once that startup routine has finished, it goes to a specific location on your cartridge and looks for the address that you want to start your cartridge to start executing code from, and that's called the reset vector. So that's the very first thing we need to set up, and it goes at the very last 2 bytes of the cartridge. So when it's plugged in, the cartridge occupies memory pages 40 hex through BF hex. It's a 32 kilobyte window. So the very last address on the cartridge is BFFF. But we need to put an address at the end of the cartridge, which is 2 bytes. So we're going to put this at BFFE. Now, for this, we're going to use the org directive. So this isn't an assembly instruction. This just tells the assembler that the next thing that appears should go at address BFFE. I'm pretty sure this is going to be common to just about every assembler out there, but maybe I'm wrong about that. So now we need to put the address where we want code execution to begin. I always point it at the very beginning of the cartridge because why not? So I'm going to use 6502 or DASM's word directive to put the address here. That's the beginning of the cartridge. So now we actually need to have something at that address. So we're going ahead, and here's that org statement again. Next thing to follow is going to go to address 4000 hex. I'm just going to put this here for now. So jump star. So what this ends up becoming, and again, this might be a DASM thing. I don't know if this is supported by every assembler. Jump star means jump back to yourself. So in effect, this instruction is just going to lock up the system. But it's something. We need to have something there. So I've done that. Now, before I go any further, I want to have a little word on byte ordering. Because now this is the sort of thing I wanted to bring up. When I mentioned I wasn't going to teach 6502 assembly, but I was going to just talk about little gotchas here and there. This is the sort of thing I was talking about. So the 6502 chip is what's called a little endian system, which means that when it comes to byte ordering, the least significant byte comes first. So this address here is 2 bytes. So the chip expects the least significant byte to be first in the pair. Now, the word directive is smart enough to do this. So when you say word 4000 like this, it outputs 2 bytes, 00 followed by 40 in that order, little endian. If I wanted to do this explicitly, you could do it using the byte directive, but you got to get the ordering right. So it's 0 like that. So these are equivalent statements. But I just like using word because it makes it clear this is supposed to be an address, and the assembler can do the work for me. All right, so this is actually a valid 5200 program right now. It doesn't do anything, but it will run. So let's go ahead and run it. So I'm going to go ahead and build it. It might crash. Actually, you know what? I take that back. It might not be valid. It might crash. But let's see what happens. Nothing. Black screen. Okay. But it's running. It's not doing anything, but it's running. And the way we can prove that it's running is by breaking into it. Now, this is very emulator specific, so different emulators are going to do this differently. But I can break the program, and I can look at the processor registers. And look at this right here. This right here, PC, this is called the program counter. This is where the processor stores the next instruction it's going to execute. And look at the address in there. There's your hex 4000. So it's currently stuck at address 4000 because that's just looping, doing nothing. So that's where it's going to be forever. But the program is built and the program runs. So there you go. There's your first 5200 program. Congratulations. It does absolutely nothing, but it's there. So before we go any further and get into some real good stuff, there is something I want to do, and it's not practical. You would probably never do this in a real program. But if you're a fan of the 5200, you got to know how this works because it's so cool you can't pass it up. Now, I have a couple of reference things open on another monitor here that you can't see on the stream, and I'm going to have to check for this because I don't normally do this in my programs, but I really want to do it. Okay, so the first thing I need to do here is I need to go to location BFFD, which is actually, you know, I'm going to explicitly org this because this is temporary code. So, and I'm going to put a byte here that is not FF. Now, this assembler fills in empty spaces with FF, which you may be wondering, okay, why is it when I ran that program, I didn't see the traditional 5200 boot up, right? With the big Atari logo and the name of the game and copyright 19 whatever Atari. Why didn't I see that? And the reason is because if the byte at address BFFD is FF, which it just happened to be because that's how the assembler fills an empty space, the BIOS looks at that and says, this is a diagnostic cartridge, and it skips that whole boot up sequence. So this is how third-party games on the 5200 skip that boot up sequence. they put an FF at this location. Now, that's probably what you're going to want to do in practice. And the reason for that is because that fancy boot up screen always says copyright 19XX Atari Incorporated. Or just Atari, I can't remember. So you can't change that. That's hard-coded in. And since you are not Atari and you are not publishing a game in the 1900s, you probably don't want that screen. Now, some games, Adventure 2 comes to mind right away. Adventure 2 hacked around this. When you start up Adventure 2, you get that screen, but the Atari has been replaced by something, and the copyright date is 2000 something. I don't remember what. Now, what the programmer probably did with that, and I think I asked him about this once to confirm it, is that when his program started up, he had FF here, so he skipped the normal boot sequence, but then he went and copied that whole startup routine out of the BIOS into memory, made the necessary changes to it to change the copyright owner and the date from 19XX to 20XX, and then ran it from memory. That's probably what he did. So that was an enormous hack. You could do it if you want to. I've never felt the need to do it. Although, I'm kind of a World War I nut, and I really want to make a World War I themed game and just slap a 1914 copyright date in there just for fun, but maybe I'll get to that someday. But anyway, by placing a byte here that is not FF, we tell the BIOS that this is an Atari game. And when I say an Atari game, I mean published by Atari game, which means it's going to run that cool splash screen. So let's go ahead and run it again and see what happens. Look at that. That did show up, right? Yep, there it is. And notice that's just running indefinitely. After a certain amount of time, it jumps to my thing, but I'm not doing anything to stop it. Like, you have to explicitly stop this screen once your program takes control. And I haven't done that, so it's just going to sit there doing its thing. But that one little byte controls whether or not you see this screen. That's where it comes from. Okay, so that being said, let's go ahead and end that. But I want to show you how to put the name and the copyright date in there, because that's cool. I mean, you can't do the 5200 without doing this once, just to see it. Okay, so the documentation I've found says that the title and copyright year go at address BFE8. I don't know this off the top of my head because I never do it. So I had to look it up, but E. Okay, so what we're going to do here is we're going to do this just for fun. So we have to put the name of the game, and we have 20 characters to do this in. And you have to use all 20 characters because that's how it spaces it out. So what are we going to call this sample game? We'll call it, oh, and you're going to do this in lowercase, and I'll show you why. Shoot and blast. So how many characters is that? It's 5, 10, I think it's 15. So I need 5 spaces. So put 3 in the front, 2 in the back. And then you follow it with your copyright year as 2 bytes. And I think this is going to be the character codes for the copyright year. I'll come back to these in a bit. We'll say it came out in 1979 because that was the year I was born. So figure out my age from there. Okay. So let's see if this worked out. What did I do? Origin reverse index. Okay, I have too many bytes. Did I put too many spaces in? Let's pull a space off. There we go. Okay. Oh, I got to put in actual spaces. Okay, I screwed it up, but that's close. All right. That's reasonably close, though. I mean, you can see how it works. I don't know why it's blinking like that. Oh, you know what? Actually, I do know why it's blinking like that. Wait, no. No, I don't know why it's blinking like that. Okay, so one of the problems you'll run into with this assembler is that when you put in strings like this, it outputs them as ASCII, and ASCII doesn't necessarily line up with the way the system is. So we got to put in, I do want to do this right, we got to put in some zeros here for spaces. In ASCII, space is 32. Here, space is just 0. All right, so how many bytes is this? 1, 2, 3, plus 5 is 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so we need 2 zeros after this. Okay, let's see if this works. Okay, I've got too many bytes. All right, I'm not sure how I'm screwing this up. Unless maybe I have to do like... I think what I'm screwing up is probably the copyright here. Maybe I just do it like this. We'll see. I'm kind of wasting time on this because, again, this is wholly impractical, but it's so cool as a 5200 fan to see how this works. So, oh, I didn't get the spaces in the middle. 19 watt. You know what? That's good enough. You get the idea. So, basically, it's the apostrophes. I can't figure out the apostrophes either. I have to figure out what the Atari character code is for those. But it doesn't matter. I just wanted to demonstrate how that boot screen works. Unfortunately, the data I picked to use is not very good. But that's how it works. So it goes to a specific location in your cartridge and looks for this information and then displays it. I'm screwing something up, but you know what? It's fine. So we're going to go ahead and get rid of this. Now, I am going to put the FF back here because I like to explicitly put this byte in here because this assembler pads everything with FFs, so I would get away with it. Other assemblers might not. So you usually don't want to leave this sort of thing to chance. Make that an FF byte so you skip the boot up screen. You know it's going to work. Now, another thing I do like to put into my games, which again is probably completely unnecessary, is at BFE 7. Oops, that's not supposed to be byte. It's supposed to be org. All right, BFE 7, I put in a 0 byte. And the, you know what I'm going to do? I'm just going to do this. Okay. So this is a flag that identifies this as an NTSC cartridge. Now, I think in practice this does not matter, but I'm always very paranoid about this. So a little bit of interesting information about the 5200 and PAL versus NTSC. So the original 5200, the one with the 4 controller ports, only supported NTSC. Never came out in PAL regions, so no problem. The later revision, the 2-port one, had a BIOS revision, which is known as the 2-port BIOS. And one of the things that changed in the 2-port BIOS was they added some code in there for an eventual PAL version of the 5200. Now, that PAL 5200 never happened. The market crashed, the system was discontinued, all that. But that code is in there, and there are checks in the 2-port BIOS that verify the region of your cartridge. I think that region check only happens on PAL systems, but I'm not sure, and if you really need this byte, don't do this. But I think that for the sake of safety, throw a 0 at BFE 7 just to make sure the BIOS knows, yes, this is an NTSC cartridge. Better be safe about it. Okay, so having done that, we've configured the cartridge to start up as a diagnostic cart, which skips the startup boot screen. Now, there is one downside to doing this, and that is that if you're not a diagnostic cart, the startup routine in the BIOS does a lot of system initialization stuff for you. But if your cartridge is flagged as a diagnostic cart, you now have to do that work yourself. So we're going to have to do a little bit of work here to get the system ready for us to do something interesting with it. So the first thing we need to do is clear the memory. You want to zero out all the memory to make sure that it's in a known state. Because when you boot the system up, what's in the memory is more or less random. It's just electronic noise. You have no idea what's in any of it. And the same goes to some extent for the 3 support chips. So what we want to do first is zero out all the memory and write zeros to everything in the 3 support chips, the GT, Antic, and Pokey. So we put everything into a known state before we start messing around with anything else. Now, to assist in this endeavor, I'm going to write a subroutine called clear page. Now, subroutine names are labels, so you put the label all the way on the left. I'm going to call it clear page, and I'm going to tag it with this word subroutine. Now, this might be a DASM thing, this subroutine tag. I'll show you what this does in a moment, though. So, how this subroutine is going to work is it's going to take a page number in the X register, and it's going to clear that page to all 0. And here's the way how we're going to do this. We're going to write the X register to FF. Now, I like to use the upper portion of page 0 as just scratch locations. So I usually reserve F0 through FF as just places to put stuff during the execution of a function. Some people use different locations, but you kind of need to have a scratch area in order to do stuff within a function. It's just a necessity. So we're going to put the page in FF. Then we're going to put 0 into the accumulator. We're going to put it into Y as well. And then we're going to write that to FE. So what we've just done is we've created a memory address at FEFF. Because remember, little endian. Least significant byte comes first. So FE is 0. FF is whatever page we're trying to clear. So this is the first address on that page that we're trying to clear. Then we create a label here called loop. Now the dot here is important, and this ties back to that subroutine directive. Labels have to be unique. Otherwise, when you use labels, the assembler doesn't know which one you're talking about. If I had 4 labels named loop, and I tried to use loop, the assembler would just say, I don't know what you're talking about. You got 4 of these things. But what this subroutine tag does is it makes every label that starts with a dot local to this subroutine until I use the word subroutine again. So this way, I don't need to come up with unique names for every single loop. I just need to come up with unique names for the labels within a subroutine. It's a very useful feature, and I'm pretty sure it's a DASM thing. I have to assume most assemblers would have something like this. Not really sure. But we need to clear this page. So how do we do it? Well, we're going to write the 0 that I know is in the accumulator to, okay, so this notation here is go to the address that starts in FE. So this includes FEFF because it's a 16-bit address. Index it by the value in Y, and then write what's in the accumulator to that location. It's like an array. If FEFF was an array, Y would be my index into the array. So we're writing a value to it, and then I'm going to decrement Y. And if it is not 0, we're going to go back to loop. So since Y started at 0, the first time I decrement it, it's going to go to FF, 256, or -1, depending on how you look at it, 256. And we're just going to keep looping. And once Y gets back to 0, now we're at the end of the loop, so we can return from subroutine and go back to where we came from. So this page, this little subroutine I wrote here will clear whatever page number is in the X register. It's very convenient. And with that in mind now, we're going to clear the RAM. So we're going to start by putting the last page of RAM into the X register, and that is page 3F. So the 5200 has 16 kilobytes of RAM in it, which is a ridiculous amount for consoles of the time. By comparison, the 2600 has 128 bytes of RAM. Not even a kilobyte, not even half a kilobyte, not even a quarter of a kilobyte, 128 bytes. It has 1/8 of a kilobyte of RAM. The 7800 only has 4 kilobytes. I don't think, I would have to check this out, but I would be, by my reckoning, I think there wasn't a console with this much RAM until probably the Sega Genesis, would be my guess. Maybe someone can correct me on that. But this system has a huge amount of memory in it. 16 kilobytes is a ton for this system. So we're going to start at the last page of RAM, and then we're going to do a loop. You know, I'm going to call this cart start. So here's where these subroutine tags come into play. You know, I think I need to put it after the org. I don't remember. So now I can put another .loop label here. And it won't clash with that other .loop label because they're separated by the subroutine tags, which is very useful. So otherwise you need to come up, because you do a lot of loops, and every loop needs a label, unless you just do a direct jump with a byte count. But without these subroutine tags, you need to come up with a unique name for every loop label throughout your program. And when you're writing a 32 kilobyte program, that gets crazy real quick. So don't do that. Anyway, so we're going to start at page 3F. I'm going to JSR to clear page. So jump to subroutine, clear page. Then we're going to decrement X. If it's positive, or more accurately, not negative, we're going to go back to loop and keep going. So we're going to keep going back and back and back until X becomes negative, because at that point we'll have gone past page 0. And so when we get to this point, RAM is now clear. We're done. It's clear. So we then want to clear the 3 support chips. So we're just going to clear those 3 specific pages they're on. I mean, realistically, we could just do the specific address, but let's just do the whole page. So we got to do page C0, D4, and E8. So we'll clear C4. Whoops. E0, or was it D0? No, it's C0, D4, E8. I'm getting mixed up. C0, D4, E8. Okay. So at this point, we will have cleared all the memory and all the chips. So we're in a known good, fresh state that we can work from. So now we're going to put our very first thing on the screen, sort of, just to make sure we're in the good. We're in the clear and everything's working. So what we're going to do is we're going to set the background color to something other than black. And this is a very useful test. This is a good way to make sure everything's just working. So the way we're going to do that, and I do want to point out, this is usually not the way you're going to set the background color, but for the moment, it's what we're going to do. We're going to load the value 0E into the accumulator. Now, I happen to know that this is the color code for white, which is why I'm using it. And we're going to write this to COLBK, color background. And then we're going to put our jump star here and just lock the system. Now, call back, color background. If you go back to the hardware file, you will find this here. This is in GTIA. There it is. Call back. This is now, so GTIA has several different color registers. It's all these here, from these all right here. There should be 9 of them. Did I miss one? Oh yeah, there's another one up here. Call PM0. Okay. So there are 9 color registers in the GTIA. So you can set up to 9 colors at once, and they're used in different areas. Call back, COLBK, this is a color of the background. So this should, when we run this now, we should get a white background, which is more than we got before. So let's see what we get. We did not get a white background, so I obviously messed something up. All right, so I'm going to try something. If this works, I will explain why. It may be that I need to do more setup before this works. Okay, and we might need to do more system setup than I realized. Okay, so yeah, actually, I'm not sure why that's not working. I feel like it should be. I wonder if there's a way I can test if we got there. You know what, there is. So one interesting way to test if you get to a location is just slap a break instruction there. I don't have a break handler set up, so this should crash the program. But at least tell us we got to that point. Oh, we're not getting to that point. Okay, so something's wrong. So let's see where we are getting to. So this is just debugger stuff, which, again, this is very emulator specific. So we can't really use this in any way, but address 0. Oh, the break instruction did fire. Okay, never mind. Okay, so I think there's more setup we need to do before we get to this point. So let's do some of that setup, and then we'll see if this color thing takes effect. So having now cleared the stuff, I'm going to refer to my Robin Banks code here. Okay, so I have a file I'm looking at, which is my code from Robin Banks that I used to initialize the system. So we're going to put some of the stuff from that file into here. We're going to see if we can get this background color change working. Let's see. Oh, I know what's wrong. Oh, yeah, I'm such an idiot. Of course there's no background. I'm not. Yeah, okay. I got way ahead of myself. I'm in 7800 mode. That would have worked on a 7800. Doesn't work here. Okay. All right, so this is going to be a bit more complicated than I thought, but that's fine. So let's talk about some of the startup stuff, and we'll go ahead and do that. So I want to go back to the hardware stuff and go to page 2. I mentioned I was going to come back to page 2 at some point. So we have all these locations here. So this is a jump table that the BIOS uses to handle certain events. What it'll do is it'll read the addresses in this table and jump to those locations. So this one here, this stands for Vector Immediate IRQ. This is the handler for what's called a non-maskable interrupt. No, excuse me. This is actually, no, I don't know what that is. Yeah, it is. That's a vector for immediate IRQ. All right. And this is the vertical blank interrupt. This is the immediate vertical blank up and the deferred vertical blank interrupt, which I'll discuss in a bit. This is the H blank interrupt, the scanline interrupt. This is the keyboard interrupt, which is used to read the keypad keys. There's two of those. They're called immediate and deferred. So the idea behind immediate and deferred is that most events start in the BIOS. So for example, I got my controller here, all right? This lovely thing. If I press the 1 key right here, bonk, it creates an interrupt. That interrupt goes to the BIOS. The BIOS then figures out, hey, that's a keyboard interrupt. How it figures that out, I don't know, but it does. And then it goes here and it says, well, what's the keyboard interrupt handler? It goes to this location here, address 208. And it jumps to this address. And there is a keyboard handler in the BIOS. So we're going to point this to a specific location in the BIOS, which I probably have a constant for down here. Indeed I do. KBD int. This is a keyboard interrupt. This is the BIOS routine for handling key presses. So the BIOS routine will do some work with that key press, some processing on it. And then when it gets done, it comes to this address here. This is called the deferred keyboard handler. And it jumps through this address to finish the work. So what you're usually going to do here is you're going to point this one into the BIOS, to the main interrupt keyboard handler in the BIOS. And then this one is going to point to something you wrote. So this is going to point to the code that for your particular game actually deals with these keypad presses. So that's the way immediate and deferred interrupts work. So immediate interrupt is almost always going to be in the BIOS, and then the deferred interrupt will be your code that handles whatever needs to happen. Now, for the moment, we're not going to have any of these deferred interrupts, but we need to point this at something. So let's go ahead and set some of these up. Now, oddly enough, this is something that if we weren't in diagnostic mode and we were letting the thing run as if it were an Atari released cartridge, This is some of the stuff that the BIOS actually does for you. All this memory clearing, it does it for you. Setting up this jump table, it does it for you. But since we're starting as a diagnostic card so we don't get the Atari logo, we have to do the work ourselves. Okay, so the first thing I'm going to do is IRQint. So we're going to use this notation here. No, it's not right. I'll explain what this means in a moment here. I think that little number octothorpe thing may not be necessary, but I'm doing it anyway. Okay, so we're setting up the main interrupt handler, which is in the BIOS. So this little less than notation means the low byte, and then the greater than means the high byte. Because IRQint is a 16-bit address, so I can't load that directly because the register only holds 8 bits, so I can't put a 16-bit value in there. So I have to load each half of it in order to put it in there. All right, so the next one we need to set up is the vertical blank interrupt, which is going to be the same pattern. In fact, some of these values are probably the same, like the high byte might be, but I'm just going to do it all the way just for the sake of illustration. Typing skills are leaving me today. That should be an L. Let me make sure I did this right. Yeah, okay. All right, so that's the vertical blank interrupt. So what that does is every time the screen has been drawn from top to bottom, the vertical blank interrupt fires. So the BIOS does some bookkeeping work here. And then when it's done, it jumps to the deferred vertical blank handler, which we'll get to in a bit. And now we need to do the keyboard handler. Actually, no, we don't, because we're not going to enable the keyboard, so at least not yet. So just don't worry. You know, we should do it anyway, actually. My categories. Stupid thing. The keyboard, not the cat. The cat is very smart. Oh, this should be a +1. Okay, so that's the keyboard handler in the BIOS. Okay, now I have a value here called endint. Endint is some code in the BIOS that ends an interrupt and returns to normal execution. So we're going to take that and put it into the deferred interrupt handlers. Because at the moment, we don't have anything else to put there, but we have to put something there so the system doesn't crash. So this is the deferred handler for the keyboard and the deferred handler for the vertical blank. And the naming here is very inconsistent, but oh well. Okay, let's make sure that builds. Unknown mnemonic sat. Where did I do sat? I did sat somewhere instead of sta. Where did I do it? There it is. Assembly is such a pain sometimes. Okay. All right, so having done that, we need to set up some other stuff. Okay, so the first thing we need to do is enable Anticdma. Now explain what this is. Now, the value I put into here is 3E. I don't remember specifically what all these bits mean. You can look this up online. Wikipedia is actually a really good source for this. Just search for Atari Antic and check out the Wikipedia article, and it goes through all the registers in detail and specifies what all the bits mean. Now, I'm writing this to a location called Dma Control. I'll talk about what that S means in a moment. Ah, here we go. Now, we also need to set up the character base. So, unlike the 7800, and of course the 2600, the 5200 BIOS has a built-in character set. So if it looks like text on the 5200 always looks the same, it's because it does, because it uses the same character set. But you need to tell Antic where that character set starts. So in the BIOS, it starts at page F8. And it's only 1 byte, because it assumes it starts at the beginning of the page. So this sets the character set to point to the normal 5200 character set that lives in the BIOS. Okay, now this is not necessary, but I'm going to do it anyway. I'll talk about PM base a little bit later, but I'm going to do this now. Okay, so now we're going to... Now this right here enables the players and the missiles, the objects that we can place on the screen. Ah, this is a very important bit. This enables the joystick reading. This is a tricky one because this, at least I know the emulator that I work with, does not handle this bit correctly. And I remember the very first time I did anything with the 5200. I got it working in the emulator. I put something on the screen I could move left and right with the joystick. I was so excited. It was the coolest thing I'd ever done. I threw it on an Atari Max cartridge, put it into my real 5200, all excited to try this out in a real system. Didn't work. I couldn't move anything. And the reason is because you actually have to enable the controllers. And this is probably a holdover from the Atari 8-bits, where you wouldn't want Pokey wasting his time scanning the controllers if your program didn't use the controllers. But on the 5200, of course, you always want that because you have no other way of interacting with the system. So make sure you do this, because not all emulators catch this. All right, now this next thing is going to enable keypad scanning. Then we need to turn on interrupts. All right, this last one we can leave behind. All right. Okay, so this is a lot of stuff. And I've kind of glossed over a lot of it because it needs a lot more work to explain it. But that's where it is. So at this point, we will have created... The system might actually do something now. Let me try it. Oh, wait. I wanted to talk about the shadow register. So right here, I wrote this thing to this location called Dma Control. So the S here stands for shadow. Now, if you look at page 0, there's a bunch of places that I have that start with this letter S. These are called shadow locations. And these shadows work in 2 different directions. So the vertical blank interrupt in the BIOS is responsible for dealing with these shadow values. So what it does is some of these things are read shadows, some are write shadows. For example, these last ones here, all these ones that say pot, these are the controller values. The pot stands for potentiometer. Now, the 5200 uses analog joysticks. So each joystick has 2 values you can read from it, the horizontal axis and the vertical axis. And this, to the best of my knowledge, is exactly how the Atari 8-bit computers read the paddles. So in effect, a 5200 controller is 2 paddles. Now, one of the jobs that the vertical blank interrupt does is it queries the Pokey chip, which is responsible for reading these values, and it puts them all in these locations on page 0. So this is where you want to read the joystick values from, these shadow values. You don't read them directly from Pokey. You let the vertical interrupt do its job, the vertical blank interrupt do its job, and it'll put all the stuff here on page 0 where you can read it. So these are what I'm going to call read shadows. Or no, right? Read. It depends on whose perspective you're looking at this from. But the vertical blank interrupt puts values in these areas, and this is where you should read your controller values from. These other ones up here are a little bit different. So these registers go in the other direction. So the vertical blank interrupt, one of the first things it does is it takes the values in these shadow registers and writes them to their proper registers. Now, I mentioned a while back that you normally don't set the background color by writing to callback like I did. What you would do is you'd write it to S callback, shadow callback. And then the vertical blank interrupt will pick up that change and it'll put it into the GT chip, but it'll do it during vertical blank when it's safe to do it. And it won't break anything because GT is not drawing at that time. It's in vertical blank. So this is a safe time to do it. Now it is actually safe to change the background color in GT at any time. And when we get into display list interrupts, you'll see that you will frequently make background color changes halfway through the screen. But you always want that background color to be restored to its original value when you start the next frame. So you put the original background color value here. And every time the frame is done, the vertical blank interrupt will grab that value, stuff it back in there, so you're back to where you started. And you can see there's a shadow register for every single one of the color registers. So changing the colors mid-screen is a very common thing to do. But you put the color you want to start at in these shadow registers, and the vertical blank interrupt will make sure that that gets reset every single frame. And there's a similar thing here for some of this stuff here. These are some control things we'll talk about. The one I wrote to, I believe, was Dma Control. So Dma Control allows you to control whether or not Antic's allowed to access memory or not. So I wrote it to the shadow register because this is one of those things that the vertical blank interrupt restores every single frame. So if I didn't put it there, it would just change it to 0 after one frame, which is not what I want. So I got to make sure it's in there. So let's go ahead real quick and try this background color thing. I might need to create an Antic display list before we see the background color, but let's try this and just see what happens. We'll write that S call back, and then we'll jump star. This might work. I'm not sure. It might not. I really don't know. Oop. I can't type. Okay, it doesn't work yet. I probably need to create a display list for Antic, which is an excellent thing to segue into next. But first, I need to get my other cup of coffee and take a little break. It's been an hour, so I will be back in a moment with more coffee. Never mind, turns out that was my last cup of coffee, so onward and upward, as the saying goes. Now, one thing I want to point out is that this is something I kind of fight with every time I start a new 5200 project. There's a lot of stuff you need to get right before you can even show anything on the screen. And it could be that the reason I'm not seeing the background stuff is because I've screwed something up. So it seems like just about every project I start, I go through a period in the beginning where I have to figure out what I screwed up. But let's go ahead and do the Antic display list. And we'll talk about how that works. So the Antic display list, and this is one of the key things about doing graphics on the 5200. The display list defines something called the play field. Now let's step back to the 2600 for a moment. On the 2600, you have a play field, which is pretty much exactly what it sounds like. It's the background, more or less. Like if you think about combat, the play field is all those walls. And it's a two-color play field. You have a background color and a foreground color. And then you have objects which are placed on top of that play field. And that same theory is applied to the 5200, but it's just more complicated. The play field is much more advanced and can do a lot more things. So the Antic chip is responsible for generating the playfield and feeding that data to GTIA so that it can be shown on the television. Now, the way you tell Antic how to generate the playfield is through something called a display list. So the display list is like a description of the playfield from the top of the screen to the bottom of the screen. Now we're just going to throw a display list in here. So we got to label it. I'm going to call it, actually I'm going to put it down here. No, well, it has to go before all this nonsense. All right, so we're going to call this, let's call it display list. We'll label it, we'll call it display list. Okay. You know what? Actually, we should give this an explicit address because there are some memory requirements for, like address requirements for the display list. Like it can't cross certain boundaries and stuff like that. So let's go ahead and put it at that address. That's fine. So the display list, again, as I mentioned, is like a top to bottom description of the screen. So Antic has a lot of graphics modes that all work in slightly different ways. And, well, you know what? Let's just do one. So almost every display list is going to start off with the following 3 bytes. $70-70-70. Okay, so what is 70-70-70? I'm going to pull up my Robin Banks display list on the other monitor just to make sure I get this right. Okay, so if you look at a television screen, there's an area on the top of the screen that's called the overscan area. And in that area, anything that you were to output up there is not guaranteed to show up on every television. So the general rule of thumb is if you skip 24 scan lines, you are now in the visible area of the screen. So the very first thing Antic Display List usually wants to do is to skip 24 scan lines. So if we look at these bytes here, if the rightmost nibble of the byte is a 0, that means skip scan lines. The leftmost nibble is how many scan lines to skip. And it's the number there plus 1. So a 7 means skip 8 scan lines. And they probably did it that way so that you can use 0, because it doesn't make sense to skip 0 scan lines. So if I put a 0 there, it would skip 1 scan line. So the 7 means skip 8 scan lines. So if I do this 3 times, I skip 8, 16, 24 scan lines. Now, the uppermost bit, the one that would make this an 8, has a special function here, which I will come back to later. And that's another reason why they left that bit open. But 70-70-70 means skip 24 scan lines. Because remember, we're going from top to bottom. So after this, I'm now out of the overscan area into the visible area. So what I want now is just for experimental purposes to make sure we're drawing something. What we're going to do now is draw something in mode E. And I'm going to point it at this address, and I'm going to talk about this here. Okay, so you know what? I'm not going to explain this right now. I'm going to do something else first just to make sure we can draw anything, and then I'll come back and explain this in detail. Okay, now I'll explain this display list in a bit, but we need to tell Antic where to find its display list. And for that, we write the display list address to those shadow registers. We have sdlist_l for display list low. And then we write the high byte to sdlist high. So if you're coming from the 7800, the display list, the Antic display list is probably best compared to the Maria display list in the sense where that defines your zones from top to bottom. that's similar, a similar concept here. And what did I screw up? SD list. Did I type those symbols wrong? It's actually list. Okay. They spelled something right for once. Okay, so hopefully this should now get us a white background. It did not. All right, so I've obviously screwed something up here. I'm forgetting something. What am I forgetting? Oops, wrong window. I apologize again. As I mentioned, you will go through this every new project because you will forget that one bit that you missed. Even when I do, like, I have a file with all these routines in it, I still screw it up every project. There's like some stupid little thing I forget and nothing shows up. Oh. It's not that, is it? Oh, if that's it, I'm going to be freaking out. That's not it. Okay. I'll leave that in there, though. It doesn't hurt. Man, what did I miss? Yeah, I'm not sure what I overlooked here. Ooh, that might be it. I doubt it, but that might be it. I don't think this is the problem, but I just looked at some of my other code and it does it this way, so let's try it. Be funny if that is actually the problem. No, it's not. Okay. Yeah, unfortunately, I don't know what's wrong. And debugging these problems is very, very difficult because it's hard to tell what you've missed in all these different registers and stuff you have to set to get anything to happen. I mean, looking at my code, it looks like everything works. Well, here's one thing we can do to test this, to find out what's going wrong. Because you know what? Learning how to debug these programs is actually an extremely useful thing. So here's what we're going to do. We're going to see if the vertical blank interrupt is actually running. So that's at address FCB0. No, excuse me, FCB8. So let's do some debugging exercises. So we're going to set a breakpoint at FCB8. Okay, the vertical blank interrupt is never running, which is definitely suspicious. But it's a clue. So I'm going to go ahead and write this to both the shadow DMA control and the normal DMA control, because my code actually does that, and maybe there's a reason for that. Nope, still not working. What am I doing wrong here? What do you think? No, I don't think that's it. All right, Kat thinks she has all the answers, but I really don't think she does. Okay, this has me stumped. And is frankly somewhat embarrassing. Okay, so let's try this. So I have this listing file, which I generate. This is part of the assembly process. I'm sure most assemblers will produce this. I want to see if I'm getting to... Let me see if I'm even getting to this point. So this is at address 4074. Let's remember that. Oh, I need to reset because it's probably already run past it. Wait, it's never getting to... Okay, something's wrong here. What is wrong here? How is it not getting to that address? Okay, we're going to have to have some adventure. We're going to have a little adventure here. Well, we're narrowing in on the cause. So we'll set breakpoint at 4000, which is the cartridge start. And we got to find out what's going on here. Reset. Okay, we've hit the breakpoint. So we're going into step mode. We're just going to see what's going on here. All right, so... Okay, so we load this. We jump into clear page. I'm going to step over that because I don't want to go through that whole process. Okay, clear page. Clear page. I want to look at what is X at this point. I wonder if it's getting stuck in this loop. 3C. No, it seems to be working. Okay. We have to do this for a little while just because I don't want to miss anything. So this is the RAM clearing. We're doing that right now. At some point, this loop should break. I'm wondering if it's getting stuck in here somehow. Okay, what is X down to now? 1C. All right, we're getting close. I could set a later breakpoint, do all that, but I really want to step through this and just make sure it actually does break out in detail. Okay, we should be getting real close here. X is down to B. All right, so it's 11 more loops. Or 10, 11, 12, somewhere around there. Learn to use a debugger. It'll save you a lot of time and effort. Oh, here we go. Okay, now we're clearing the chips. Okay, now we're continuing. Setting up all the stuff. Okay, now we got there. Huh. I wonder why I wasn't getting there before. Interesting. Oh well. This is a bit of a mystery. I'm not sure where the flaw is in this setup code. I do apologize to anyone watching this. This should have worked. I don't know what I screwed up here. I mentioned before, I've started learning the 7800, and just getting that thing to draw anything took me days of getting the configuration totally right. And this is a system I've done several games on, and I still screw it up. It's actually really hard to get this stuff perfectly right. It looks like I'm not starting up Antic somehow. I'm not sure what I'm missing to do that. I mean, that's my guess, is that for whatever reason, Antic is not working. So, one way I can test that is if Antic were working, it would be trying to read from address 2000. So what I'm going to do is set a watch point on address 2000, see if anything tries to read from that address. Now we should get one hit right away during the memory zeroing routine. Okay, let's make sure that's where I am. Yeah, actually, I don't even know if this is going to pick up Antic. Yeah, this is in the memory zeroing routine. Okay, I don't know what I did wrong here. Oh, cannot type today. Okay, it's not picking up those reads, but you know what? I'm honestly not sure it would. Oh, okay, this is a mystery to me. All right, let's try writing this to both display list. Locations. I don't see why this would work, but let's try it. Nope, still nothing. All right, well, if I can't solve this in the next couple of minutes, I may just have to leave this as it is and come back next week with a solution, because I don't know where I went wrong here. My impression is definitely that for some reason the vertical blank interrupt is now running. Now it could be that this is wrong. Did I do this wrong? Huh. Nope, I am completely stumped on this one. It's unfortunate, but it's true. I have no idea what's going on. So, for lack of anything better to do, I think I'll talk about the Antic display list and how it works, because I might as well talk about something. So, since I can't seem to get it working, let's do this. No, we'll talk about this one. So, the display list is, as I stated before, it's a description of the screen from the top to the bottom. And I already explained what this particular value does. It just skips a bunch of scan lines. But here's where we get fancy. So the general format for a byte in the display list is that the low nibble here specifies a graphics mode. And the high nibble is a set of 4 bits that do something special on that, in that particular mode line, as it's called. So Antic has a huge number of graphics modes. And each graphics mode has a certain number of properties and takes up a certain number of scan lines vertically. Now here I'm using mode E. Mode E is 160 pixel bitmap mode. So this just reads raw graphics data 160 pixels wide and puts it on the screen. So every single occurrence of 0E like this is another line of mode E as we move from the top of the screen to the bottom of the screen. Now, mode E is only 1 scan line tall. So now ignore this stuff here for the moment. So I have 16 lines of mode E. So if this were drawing correctly, after that initial 24 line overscan, we would have 16 scan lines of 160 pixel mode. Now, this thing at the end here, there is no mode 1. So if the right digit, the right nibble of the byte is a 1, that means that this is a jump instruction. And the high nibble indicates the details of that jump. So 4-1 means wait until the vertical blank, so wait until the screen is finished, and then jump to the address that follows. In this case, the address is display list, which is back up to the top. So this is how you terminate a display list. And it's very important to terminate a display list. And that bug has bitten me in the past. So you're pretty much always going to end a display list with 4-1 and then the address of the top of the display list, because it goes back up there and then starts the next screen, the next frame of the screen. Now this is a little bit different up here. This 4 here means following this instruction will be 2 bytes that represent the address from which Antic is going to start reading the data that is actually going to put on the screen. So this says, I want a line of mode E, and you're going to start reading your graphics data from address 2000 hex. Because remember, little endian, least significant byte comes first. So I would stuff my graphics data into 2000, and it would start reading from there. And it keeps reading from there until you change it, mostly. So these following mode E lines would just keep right on going through memory and displaying whatever comes across. Now, most mode lines take 40 bytes of memory to specify what's in that line. Some take less. I don't think there are any that take more, but some are less. So I think what I'm going to do, actually, just for the sake of demonstration, is I'm going to show you something from Robin Banks, which is my project that I'm just finishing up now. And I'm going to show you the display list from that and how it runs. So we're going to go over to that directory. And then we'll go ahead and start up Rob here. So this is Robin Banks. This is my game that's pretty much done. I just lost my window here. Okay. All right, so we'll put it right here. So I'm going to show you the display list for this screen. So that you can get an idea of how these display lists work, because this really is the heart of the system. So here it is right here. This is the title screen display list for Robin Banks. So this list here describes this screen that you see on the left. So let's go through this line by line and explain how it works. And that's probably where I'm going to end the video. And before next week, I'll figure out what's wrong with this code and why it's not drawing anything, and I'll present the solution next week, and then we can start doing more interesting things. So first off here we have, as I specified, byte 707070. This is skips 24 scan lines, so you come down into the visible area. Then underneath that we have this. So as I said before, the right nibble is the mode, the graphics mode. So graphics mode 2 is 40 column text mode. So if you look at the top of the screen here, you see that line with the scores on it. That is one mode line of mode 2. And this is where it's important to separate the difference between a mode line and a scan line. A mode line can have many scan lines. So here, a line of mode 2 occupies 8 scan lines. Actually, is it 8 or is it 10? It's 8. It's 8 scan lines. So this one line of mode 2 occupies 8 lines. And here I have that 4-bit. So the 4 means following this is the memory address you should read from. In this case, it's reading from address 2000, just like it was before. So it's pulling up one line of mode 2, which is 40 columns of text. Now following that, I have another line of mode 2, which I'm just using for spacing. I could have used a 70 here, but I used 2 for some reason. I don't remember why I did that, but I did. So this, after the score line, there's just a blank line. So I'm just doing some space, but I'm setting this 8-bit. I don't want to go into super detail on the 8-bit right now, but the 8-bit calls for what's called a display list interrupt. So what happens here is that while I don't remember the exact location where this happens within the mode line, but at some point in this mode line, Antic's going to tell the 6502, hey, do your thing. So it wakes up the 6502 because it halts the 6502 during its processing, but it wakes it up and says, here's that interrupt you asked for. And now the 6502 can change things about the screen in the middle of the drawing. I talked back about the 2600 about how this is standard practice on the 2600. This is like all you do. But on this system, you can request this at specific locations to change things. And what I'm specifically changing here are some of the colors, because the playfield colors need to change from this text area to this area down here where I have the title logo, because I need different colors there. So this interrupt, I'm not going to go into the code that does this. We'll cover that later. But this interrupt changes the screen colors. And then we have a byte of mode E, which, as I showed you before, is that high resolution 160 graphics mode with a memory change. So I'm pointing to a different location in memory. I point it to a word called title logo. Now this is an interesting one because the title logo is actually in the cartridge. So at this point I'm telling Antic, get your data from the cartridge. Don't even get it out of memory. We're getting it from the cartridge. And then we have a whole bunch more mode E lines. So these mode E lines, all the way down to here, are the entirety of that title logo. It's just a whole bunch of lines of mode E. And then here I'm skipping 7 lines and asking for an interrupt. So this is the 70 line, the skip 8 scan lines, but I turned on the high bit, which turns this into an F, because I want another screen interrupt here. Because now that I'm done with the logo, I need to change the colors back, because I'm going back to text mode. So I need to change the colors back so that the text looks right. So I do that here in this space between the logo. And that's something you'll find when you're doing your display list, is you need to find places to make space so that you can do these interrupts and change colors and things like that where you have the room to do it. So I've got some space here, and here I change the colors. And then we come down back to mode 2 with an address. So we switch it back. Now we're looking at address 2140 for the text. So now we're at the point in the screen where you see where it says game mode, 1 player, all that kind of stuff. And you see there's more lines of mode 2 that follow this until we get here where we switch to mode 4. Now mode 4 is a, how would I describe it? Mode 4 is another text mode, but it's a slightly different one. It's multicolor characters, and actually looking at this now, oh, okay, I remember how I did this. Sorry. You forget how you do this sometimes. This interrupt I requested back here is still running. It hasn't ended. So somewhere in here, it actually changes the character set. Remember that CH base value I started that told it where the character set was? Somewhere in this mess, it changes the character set to point to somewhere else. And that's where this little hat is coming from. It's from the custom character set in the ROM. So it changes to 2 lines of mode 4, which is that hat. And then we go back to more mode 2 for the rest of the screen, which is all the text on the bottom. And at the end, and somewhere in here would switch the character set back to the default character set. And then here at the bottom, we have wait for vertical blank, jump back to the top. So this is an example of a full actual in-use display list and the sort of things that you do with it. The primary function, as I said, is just a mode description from the top of the screen to the bottom of the screen. But there's a lot of other stuff you can do in here where you can, you can have interrupts, and you can change colors and change where the memory, where it's reading memory from, and all that kind of stuff. But I wanted to give an example of an actual display list from a real game so you can see how this works. And this, they can get very complicated because this uses, I guess the key thing to take away from this is that Antic has a lot of graphics modes, but you don't have to commit to one for the entire screen. You can mix and match. You can change modes as the screen moves down and have a variety of different things. Like there are 3 graphics modes going on here. There's the 40 column text, the multicolor character mode for that little hat, and then a bitmap mode for the title logo. So 3 different graphics modes going on this one screen. And the Antic list is what you use to organize all this and to tell it, hey, this is how I want the play field to be displayed. Which brings me to another point. This is all play field. Now, in addition to play field, you have things called players and missiles that you can move about on top of the play field. And you know what? Just for the sake of demonstration, I will go into the game here. Now, within the game itself, I'm going to pause it. Everything you see here is play field, with the exception of the player and the 4 cops. They're all sprites, player and missile objects. So the player is one object. 3 of the cops there are 4 player objects. One is the actual player. The next 3 are the green, yellow, and blue cops. And then the red cop is actually a collection of objects, which are called the missiles. So the players are 8 pixels wide. And the missiles are 2 pixels wide. Now, the way the player and missile colors typically work, and I'll cover all this again when I actually get the main program working and we can start playing with players and missiles, but each player has a single color assigned to it. And that is, if I go back to this hardware file, if you look at GTIA, here we have color PM0. So PM0 stands for player missile 0, which in this case is the actual player. This is Rob the Thief. So under ordinary circumstances, a player and its associated missile share the same color. But there's a mode you can turn on that's called fifth player mode, which gives all of the missiles their own independent color. But there's one color for all 4 missiles. So I'm using fifth player mode here in Robin Banks. And the missiles are all set to the red color. And then I put all the missiles side by side because they're 2 pixels wide. So if I put all the missiles side by side, it's like I have another 8 pixel wide player. So that red cop is actually the 4 missile objects all moving together in fifth player mode. Now you may be thinking, well, if each player has one color, how does Rob have all those different colors on him? And the answer to that is display list interrupts. So there's one of these display list interrupts running for the entire height of the screen that changes the Rob player's color at the appropriate points to change his color. If you look closely at that sprite, you see the colors are all in horizontal bands. And this is very typical of 2600 games as well, where the multicolored objects the colors would be banded horizontally, because as the scan lines go down, it's just changing the color. And that's the same technique that's being used here to color Rob. So that's why he looks the way he does. Now, I couldn't do that to the cops because of time. You don't have very much time to make these changes. And the amount of time you have to make these changes depends on the Antic display mode, the Antic mode, because some modes are faster than others for Antic to process. And as it turns out, the graphics mode I'm using here for the playfield is actually one of the slower ones, which I didn't know when I got into this, because I had some big plans for some screen interrupts that I was not able to do, because I didn't realize how slow this graphics mode was. So I wasn't left very much time to do things in my interrupts. I had enough time to color Rob, and that's pretty much it. I didn't have enough time to do anything else. I really wanted to do more, but I just couldn't do it. If I was using a different graphics mode, maybe I would have had more time to do some other things, but it just didn't work out that way. So I had to just color Rob. But you know what? That's how that works out. And again, once I figure out what's wrong with the code we've written here, we'll go into this in more detail and actually start playing with the players and the missiles and all that kind of stuff. But unfortunately, for now, I think I might just have to call this a bit of a bust for where it is right now, because I don't know what I missed. And we have to go through this code and figure out what I missed and get it working again. But it's been pretty close to 2 hours now, so I think I'm probably going to call this a day. And then I'll have a week to figure out where I screwed up. And we'll get this working. So next week, we'll dig back into this, and hopefully I'll have some working code by then. And I'll point out exactly what I screwed up so everybody knows. And we'll start building something. We'll get some stuff going on and start working with it. But I think one thing to take away from this is that just getting this console to do anything is a lot of work. You have to do a ton of work to get anything on the screen at all. And this is not just true of this console. I think I mentioned earlier, I have just started playing around with the 7800, and it took me weeks to get anything because I was just screwing it up. I downloaded a demo. I was following the demo, trying to do exactly what the demo was doing, and I still screwed it up. And that's more or less what I was doing here. I was following my code from a working game, the game I just showed you, and somehow it's not working. I've missed something along the way. So I will try to figure out what that thing is that I missed along the way. And hopefully by next week, I'll have figured it out. So we'll start off next week with working code, and we can go into detail on what I screwed up, how I screwed it up, and then we can start looking at actually messing around with the graphics, getting something on the screen, maybe something we can even move, and then we'll see where things go from there. So for this week, I'm going to be saying goodbye, and hopefully next week we will have some better luck with this and be able to press forward in our simple little shoot 'em up game that I want to make. So that'll be it, and tune in next week where hopefully we'll have better luck. Goodbye for now.